Good morning, everyone. Today we are going to see the Microcanonical, Canonical, Grand Canonical Ensemble. Myself, Dr. J. Sheila, Associate Professor of Physics, Fatima College, Madurai. Let me start with the state of a system. The state of a system, which can be defined by the three state variables, that is, pressure, volume, and temperature, which can define a system at equilibrium. Adiabatic system, which can be mentioned as, which will not allow any kind of heat into the system and also outside the system. As you all know, the diathermal system, that might be no heat exchange. So mostly the kind of system which may have more number of molecules or atoms with a variation in temperature and also variation in the volume might be considered with variation in pressure. So this is, as you are looking, the kind of thermodynamical system which has more number of atoms or particles inside, which can have the random orientation. So which can move anywhere inside the system. As temperature increasing, the entropy of the system also increasing. So for any kind of system, for the efficiency of the thermodynamical system, the entropy has to be controlled. But for most of the cases, the entropy cannot be decreased. That is the concept as per the law. Here also, due to the variation in temperature, due to the variation in pressure, and due to the variation in volume, so always the entropy goes on increasing. As entropy increases, the system is not good. If you are reversing the condition, if you are going for the system with reversible cases, you can attain 100% efficiency. So always, for most of the mechanical system, for most of the thermodynamical system, we are expecting 100% efficiency only. So in that way, we need to control the entropy by properly varying pressure, volume, and temperature. So this is the case. This is also the another kind of distribution in many kind of assemblies, how the particles are distributed, right? In some assembly, that is one or two particles, some boxes, there are three particles, there are two particle or one particle. So as we know, more number of particles we have for the maximum level. So that can be distributed in that way. Now coming to this again, always the entropy factor is very much important. You all know the particles are arranged in an irregular way. So as temperature increases, again the particle distribution is completely irregular. So what will happen? The entropy will goes on increasing. So the value of S equal to Kb ln omega. So this is the thermodynamic probability which depends on the microstates based on the macro state. So where d is equal to T ds minus P dv. So as you look at the picture given on this screen, so the whole grid can be divided into two ways. This is the kind of assembly where we are having E1, V1, N1 is constant, and in the second sector also E2, V2, N2. In that way, overall, the whole system can be divided into many assembly, and assemblies of assemblies can be called as ensemble. as you all know. Here, total energy can be related to E1 plus E2. The volume can be calculated from V1 plus V2. And N, the total number of particles, can be taken from N1 plus N2. When we look at this picture, where we can see what about the microcanonical and what about the canonical and what about the grand canonical. So here, what are the parameters are constant for canonical and for microcanonical and grand canonical. So here when you look at grand canonical, the mu refers the chemical potential, V refers the volume, and T refers the temperature. So these three might be constant. So one of the relaxation possible from microcanonicals are energy can be shared and the number of particles also can be shared with another partition. And with respect to canonical, so the number of particles again constant there as microcanonical, and V also, the volume also can be maintained constant and temperature remains constant here. One of the relaxations from microcanonical is for our convenience, the energy can be exchanged with the neighboring states. Here, clearly you can look at the microcanonical distribution. So where we have the regular ensemble, as you all know, the assemblies can be called as ensemble. Here also many assemblies are there. So the system can be distributed like this, can be divided like this. So where we have to keep N, V and E are constant, and for other cases we may go with some relaxation. So here N, V, T are constant for the next case. So little bit of relaxation between microcanonical, canonical and grand canonical. So from this overall, the thermodynamical properties can be studied. So from this observation, so the value of omega, the ratio of microstate to macrostate also can be calculated from this derivation part. So S refers here, that is the entropy, where we could find the value of S as Nk log some factors plus 3 Nk by 2. So overall the derivation, when you want to go with how we can find out the entropy for the particular thermodynamical system, this way you may proceed. And here also another cases, the value of with the help of entropy, another statistical temperature variation also can be calculated, which is very much related to internal energy. So for that we have to go with the differential equation dou sigma by dou E. So from that we can calculate what about 1 by tau, so which is equal to dou sigma by dou E. So just you look at the equation and find out. And another cases, some kind of relation can be maintained between the statistical temperature and thermodynamic pressure, that also can be seen in this slide. And one more factor has to be explained for the thermodynamical system. So when you have a system that can be divided into two systems as 1 and 2, there is some small partition is there. So what will happen for the entropy? That might be the another question in your mind, right? May come. So almost there are two cases are possible here. One might be the gases which you are taking for the two cases. 1 and 2 might be equal and 1 might be unequal. But for unequal cases, always the entropy can be readily increased. That you all know. Yes, as per the Gibbs paradox. But for the same gases, if you are taking in 1 and 2 system, what will happen? Again, the entropy is increasing. Yes, that is called Gibbs paradox. But for that, Gibbs identified as what can be the possible assumption can be made is the particles are indistinguishable. When you assume as particles are indistinguishable, you can maintain the entropy variation. Otherwise, you can't maintain the entropy variation. As we said earlier, so always in most of the thermodynamical system, entropy is increased. I think we can conclude with this Gibbs paradox. Thank you.